Okay, wrapping up the last part of the notes here in chapter 6, been talking about binomial random variables and how if the sample size is large enough where you can show that the expected number of successes and the expected number of failures is at least 10, then it means the shape of the distribution is normal and you could use normal calculations. So we're going to review that here with this example, and then I'm going to introduce you to a geometric random variable here to wrap this up. So here this is discussing that in a survey of 506 teenagers, so that's going to be our N, our number of trials here, ages 14 to 18, subjects were asked a variety of questions about personal finance. One question asked teens if they had a debit card. Suppose that exactly 13% of teens aged 14 to 18 have a debit card. So that's going to be our P, our probability of a success. Okay, we're going to let X, our random variable, represent the number of teens in a random sample size of 506 who have a debit card. That is what we're defining as our success here. Okay, so first it asks, is the distribution of X binomial? Okay. And then there's this question that got crossed off. I shouldn't have crossed it off. And then it asks, well, is it approximately binomial? Okay. So let's go ahead and look at this here. We're going to say that a success is if you have a debit card, and a failure is no debit card. Now, keep in mind, when we talk about surveys like this and we're selecting people, the idea is when they're choosing these 506 people and they pick one at a time, they don't want the person who they just selected to be put back into the poll so that they would accidentally be selected again. And so anytime we're doing a survey, the assumption is always that we're doing that survey without replacement. Okay, and that's where this was kind of coming in. If there's no replacement, usually that independence condition is violated. And so we would say, well, the distribution of the random variable X, it's technically not binomial, but we can get away with considering it to be approximately binomial if we can show that the 10% condition has been met. Okay, the 10% condition. Remember, the 10% condition is making sure that our sample size is small enough that if we were to multiply it times 10, it would still be less than or equal to the population size. Okay, that means if we're just surveying a small portion of all of the teenagers who exist, it's not going to make a big enough dent in the fact that we're not actually replacing them in between when we pick another one. And so we want to take 10 times 506, and we want to show that that number is definitely less than all of the teens that are between the ages of 14 and 18. And of course, there are way more than 5,060 teens between the ages of 14 and 18. So we're pretty safe with saying that this independence condition then is roughly met here. Okay, you always have to show the 10% condition if you are sampling without replacement. Okay, our sample size or number of trials is 506, and the probability of a success is 13% is what the odds are of someone having a debit card. Okay, so we're going to call this one yes. We're going to say it's approximately binomial because the 10% condition is met for independence. Okay, for independence there. Oops, sorry. Lost my spot there. All right. Now, for part B, it says, is the distribution of X normal? Okay, well, to test the normal, to see if it's normal, we have to use what's called the large counts condition. Okay, these two conditions, the 10% condition and the large counts condition, is something that is continually going to pop up in future chapters. We're going to be using these a lot. You guys will have these memorized here for sure. Okay, here's what we have to show, and of course on the AP test you don't have to be writing this down, but what has to be shown is that if you take the number in your sample times the probability of a success, that's going to come out, and again, this is the expected number of successes. So in 506 teenagers, we would expect roughly 65.78% of them to have a debit card. And then over here, we're taking the number of trials times the probability of a failure, and in 506 teenagers, we would expect roughly 440.22 of them to not have a debit card. Okay, we have the number of expected successes and the number of expected failures are both showing that they are at least 10. So that is where we would say the shape of this distribution would have to be approximately normal. You really should be using the word approximately here. Okay, it's generally not exactly normal, but it's good enough, so we call it approximately normal. Okay, so then we're asked to use the normal distribution to estimate the probability that 60 or fewer teens in the sample have debit cards. Okay, so here's the probability we're looking for here. 60 or fewer, so that means less than or equal to. Okay, now we established that it was normal, so that means we're going to be able to use the normal CDF feature. Okay, we know the lower bound comes first and the upper bound comes second. Oops. So the lower bound would be the negative 10,000 since this is a less than problem. But what I need for the mean and the standard deviation would be to calculate the mean for this binomial random variable and then the standard deviation for this binomial random variable. Again, these formulas that I am writing down, they are on the formula sheet. You would not on the AP test have to show the formulas. You just need to show the substitutions on your paper. Okay, so we are plugging these values in. We would then transfer these up here as our mean and standard deviation for our calculator inputs, and then we would report that roughly 22.23% of teenagers that there's a 22.23% chance that out of 506 random teenagers that were surveyed, that 60 or less of them would actually have a debit card. Okay. Now, the next part to this asks, they want you to compare this answer when we used the normal CDF feature to the answer we would get if we used the binomial CDF feature. Okay, so if we were going to do the binomial CDF feature, obviously this is a less than or equal to, which is really what the binomial CDF feature is designed to calculate. It's designed to calculate a less than or equal to. So we put our three inputs in, and you notice that these answers, they might feel like they're different. I mean, clearly they are here, but as far as on the rubric on an AP test, they would accept either of these two answers, of course, with the supporting calculator inputs for either of those two would be completely fine. Okay, on the next page, we're going to kind of go in a slightly different direction here. We're going to just briefly look at a geometric random variable. You'll notice there is an acronym as well off to the side here. All of the variables are exactly the same, except instead of bins, this is called bits. Okay, now I want to draw your attention here to the description at the top. When we're talking about a geometric setting, we're talking about this arising when you're performing independent trials. Still have to have the same chance process, so your probability of a success still has to be exactly the same on each trial, just like with a binomial random variable. But here's the difference. You keep going and you record the number of trials until you reach a particular outcome that you're looking for. Okay? See, in a binomial setting, the number of trials has to be set. It has to be fixed before you perform the probability. But in a geometric setting, you are trying to count the number of trials until that very first success would occur. Okay? So the key is you keep doing something repetitively until the success happens. Let's read through a few scenarios, and I think you can kind of tell as you read through these that this is clearly this is talking about needing to do something until a specific event would occur. So we are looking in a geometric random variable to see what are the number of trials needed for us to get that first success. So maybe the question is, how many M&Ms are drawn until a blue one is selected? Or how many students will I draw from a hat until I pick a senior? How many households can a surveyor call until someone answers? Okay, so we're just going to look at an example here of sort of how this works. We're talking about the probability that the kitchen serves those fantastic snickerdoodle cookies for lunch is 0.3. Okay, so 0.3 is representing the probability of a success. Okay, and if we were to go through our acronym here, the B, of course, a success is to serve the snickerdoodles. Okay, so we'll say snickerdoodles, and a failure would be no snickerdoodles. Okay. Now, as I read through here, it says, starting at the beginning of the week, we want to find the probability that it takes 4 days before we finally get the snickerdoodle cookies. Okay, you can tell as you read through this, this is talking about until we get the snickerdoodle cookies. Okay, now here's one thing that I'm going to do before we go through the acronym here. Usually when we talk about a geometric random variable, just to kind of switch up the variable used, we use a y to represent the geometric random variable. And here we're looking for what's the probability that it would take 4 days before we would get a snickerdoodle. Well, I mean, there is a calculator command for this, but to be honest, the geometric PDF, which is what you would be using if you were doing just an equal to problem, is really not something that you need to mess with on the calculator, because we're talking about them failing to serve snickerdoodle cookies on the first day. Now remember, them serving it is 0.3, so if they're not serving snickerdoodles, it's 0.7. Okay, so the first 3 days are all failures. They're not serving snickerdoodle cookies until we get to the 4th day where they serve it. That's what this was saying. When we say y equals 4, we're saying that it took 4 days before we got the success. That's what the N would, or the T would be here, that we're looking at 4 trials, okay? And then, of course, the probability of a success was 0.3 here, and we're just assuming independence on this here. Okay, so this multiplies out to be 0.1029. Now, if you use the calculator feature, it wants 2 inputs. It wants you to just put what the probability of a success is. So this is just underneath where you find binomial PDF and binomial CDF. If you were to use this feature, you would need 2 inputs. Again, I would discourage you from doing this just because it's so easy to do the problem without messing with the calculator. Okay, and the Y is the trial when you get the success. Okay. Oops, I labeled underneath here wrong. Underneath the 0.3 should be the P, this should be the Y, and that would be the 4th trial. Okay, and you get the exact same answer. It mentions down here the PDF is so easy that the calculator feature is really not even needed. One that's a little more valuable would be the CDF feature, if they would say something like, what's the probability that, and we're looking for, like a less than or a greater than. Or I'm sorry, a less than or an equal to there, okay? All right, so if we verified that, which I kind of did that just up here, okay, I verified that on the calculator. That's what I did right there, okay? All right, the last thing that we're just going to take one brief look at, and these formulas are on the formula sheet, is how to calculate for a geometric random variable the mean or the expected value. Okay, the formula is simply the reciprocal of the probability of a success. Okay, so if you're looking for the average or expected value for that geometric random variable, it's just going to be 1 divided by the probability of a success. Okay, and so what that means is the expected number of trials that it would take for you to get that first success. On average, it takes, that many trials, whatever you'd be getting for your expected value. Okay, and then the standard deviation is represented by this formula, which you can see. You just plug in the probability of a success for those P's. Okay, so in this example here, it says suppose that you're an 80% free throw shooter. You're going to shoot until you make it. The probability of a success is 0.8. That means on average, if you do 1 divided by the probability of a success, it roughly takes you 1.25 trials before you are successful at making a shot. Okay, it means that we would expect the shooter to take 1.25 shots on average until he makes his first shot. Okay, and then you could calculate what the typical spread is there. Okay, I believe that brings this section. Oh, one last thing on just the very final page here. Just kind of comparing binomial random variables and geometric random variables. And honestly, here is the major difference. Binomial, the trials are fixed, and in geometric, you keep going until you hit that first success. But the last thing here with these two graphs is really just comparing their shapes. Okay, we know that if we're talking about the shape of a binomial random variable, it does become roughly symmetrical as your sample size increases. Okay, like it becomes approximately normal when we can show that large counts condition. However, and I've seen this on multiple choice questions, the shape of the distribution for a geometric random variable is always skewed to the right. Okay, and the logic there of why it is always skewed to the right is because we're looking at, this is the number of trials along the x-axis that it takes until you get that first success. Okay, the more trials that it takes to get that first success, the less likely that it would take more trials. And so you can see that this probability is going down as you move across here. Okay, the likelihood of you getting a success is much higher here at the beginning, and then if it keeps taking longer, for example, let's say that you were going to flip a coin and you were going to say that heads was a success. Okay, it would be very rare for you to flip the coin, say, 20 times, and you kept getting tails, 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 tails. Okay, so we always expect that success to occur, somewhere early on, and it takes, the probability just continues to shrink if you're saying that it's going to take much longer to hit that first success. And that's what causes the shape of the distribution for a geometric random variable to always be skewed to the right. Okay, that brings this chapter to a close, and there